Hello everyone. I hope you're well and I hope you're ready to do some more chemistry. Today we're going to have a talk about the second homologous series on our list, the alkenes. Very easy to get this mixed up with the alkanes. They're very similar words, just one letter difference. So it's important that we really are careful when we're writing down names of these compounds and we can distinguish between the two different homologous series. Our learning intention today, just as I said, we want to explore the alkenes as a homologous series. We'll have a little look at their general formula. They've got a different general formula from the alkanes, and we'll talk about why that is. We'll revisit this idea of saturated and today unsaturated bonding, and we'll also have a little talk about some of the uses of our alkenes as well. Oh, and I'm sure we'll also be drawing and naming quite a few of them as well, so let's not forget that. The alkene family is a homologous series, just like the alkanes, only this time their last three letters, their second name, if you will, the last three letters end in E-N-E, not A-N-E. So it's a very, very subtle difference, and it's a slight pronunciation change as well. When it's E-N-E in this case, it's the alkenes, and the last homologous series that we looked at when it was A-N-E was the alkanes. So very small, subtle differences, but we need to make sure that we're happy with them. We need to make sure what each homologous series looks like and their properties, etc. This is our second homologous series, and don't forget that definition of homologous series is important. It's a group of compounds with the same general formula and similar chemical properties. And speaking of general formula, the alkenes general formula is different from the alkanes general formula. And we'll have a little look and figure it out in just a second. And we'll see why. So what are some names of some alkenes then? Well, we could have something like propene, or butene, or ethene. Now, these will look pretty similar and very familiar to you, hopefully, when we compare them back to our alkanes. The only thing that's changed is this third to last letter is now an E instead of an A. So what does that mean? Well, that means that we've got an alkene and not an alkane. But what does it tell you about the structure, and what does it tell you about these compounds? It tells you that all of these compounds contain a special type of bond called a carbon to carbon double bond. A carbon to carbon double bond. And that basically means exactly what it says on the tin. We have got a carbon bonded to another carbon, but not like we've seen it before, not with just one covalent bond between these carbons. There are two covalent bonds, so two shared pairs of electrons between the carbons. And every single alkene, propene, butene, hexene, octene, etc., every single alkene always has one carbon to carbon double bond. So let's have a little look at drawing one of these and seeing what it would look like. So let's take ethene. Let's have a little look at our chemical structure, our full structural formula of ethene. Now we should know from the prefix eth that this has two carbons in it. Now our last three letters are not A-N-E, so it's not an alkane. This time it is E-N-E, so it's an alkene. And that tells us that we've got what? Well, we've got this carbon to carbon double bond. So let's pop that in between these two carbons. Now, if you remember back to those rules that I talked about, every carbon within a molecule, every carbon wants to make 4 bonds, and every hydrogen only wants to make 1 bond. So let's have a little go at completing the rest of this. First carbon, it has already got 2 bonds on it, so it needs another 2. It needs 1 bond and then a second bond. now this carbon, the first carbon here, has 1, 2, 3, 4 bonds. Well, that's exactly what we wanted. Going to the second carbon, that's only got 2 bonds, so that'll need a further 2 bonds. And now we can pop in our hydrogens on those open bonds there. And what we've drawn is ethene. This is ethene, and its chemical formula or molecular formula is C2H1234. Let's quickly see how that compares to our alkane equivalent if we had ethane, and if we remember what that looked like in its structure. So ethane again would have 2 carbons, wouldn't have a carbon-to-carbon double bond though, because it doesn't end in ene. This is an alkane, it's ane, so we've only got single bonds. It's a saturated molecule this time, and ethane should look like this. And if we compare the two structures, they're quite a bit different. We've got 2 less hydrogens, and that's obvious as well if we looked at the molecular formula. Ethane is C2H6, whereas ethene is C2H4. I don't know what happened to that 4. Oops. C2H4. So what does that show us? Well, it shows us that the alkenes with their carbon-to-carbon double bond require less hydrogens in their structure, whereas the alkanes, where they don't have a carbon-to-carbon double bond, will have more hydrogens. Now let's have an explore into working out a general formula for our alkenes. So hopefully we still remember that the general formula for the alkanes is CnH2n plus 2. Let's try and figure out what it would be for these alkenes now. So we've looked at the first one here, we've had a little look at ethene. Let's look at 2 more. Let's do propene, and let's look at butene as well. So our prefix on this chemical is prop. It would tell us that we've got 1, 2, 3 carbons. Now we know, because of the last 3 letters, that it is an alkene this time, not an alkane, it's an alkene. And if it is an alkene, it must contain a special bond, a carbon-to-carbon double bond. It has to contain one of these in the structure. I'll put it on the first carbon here. We'll talk about where and why you'd put it in different places later on, but let's just keep it on the first carbon right now. And there's only one of them. We wouldn't draw something like this for propene. It doesn't have 2 double bonds, it's only got 1 double bond, so between the second and third carbon I'll just put a single line. And now we can fill in the rest of the hydrogens. Every carbon, remember, wants to make only 4 bonds. And if you do this step, if you don't get lazy and do this step, you'll never draw a structure incorrectly. And it's quite important that we do this and we don't just put in hydrogens and loads of lines everywhere, because what I've drawn there is wrong. Look at this first carbon, it's got 1, 2, 3, 4, 5 bonds. This second carbon's got 1, 2, 3, 4, 5 bonds as well. We don't want to do that. We can't just rush in and throw in bonds. So take your time and count to 4. Shouldn't take you long. So the first carbon, we've got 1, 2, needs another 2 bonds. 3, 4. Second carbon has 1, 2, 3 bonds on it already. It only needs 1 more line. And then our last carbon needs 3 more to make 4. Now we'll put in our hydrogens on the open bonds. And now we have drawn the full structural formula for propene. Its molecular formula would be C3H6. It's got 1, 2, 3 carbons and 1, 2, 3, 4, 5, 6 hydrogens. Okay, butene now. But tells me that we have 4 carbons. There's my 4 carbons. Last 3 letters tells us that it must contain 1, carbon to carbon double bond. I could put it in the middle, I could put it in the end, but I'm going to put it on the first carbon. And again, we'll talk through how and why and where to put it later on. Let's just look at a more simple case right now. Put it on the first carbon. It only contains one carbon to carbon double bond. There, it's there. So we'll put a single bond between the other carbons. And now we go through and count to 4. First carbon here has only got 2 bonds. 1, 2. It needs another 2. Second carbon has got 1, 2, 3 bonds on it. Needs another 1. Third carbon, it's got 2, needs 2, and the last carbon, well, that needs 3. And we can go in and we can fill in our hydrogens on these empty bonds now. And now we can get the molecular formula. C4, H1, 2, 3, 4, 5, 6, 7, 8, H8. Now we should hopefully be starting to see some sort of pattern emerge here, and the relationship between the number of carbons and hydrogens, and it shouldn't take a genius to work it out. Let's go back up and look at ethene. It was C2H4. Now we had propene and butene. That was C3H6, and butene was C4H8. Hopefully we've recognised now that the number of hydrogens is always 2 times or double the number of carbons, and that will allow us to have a general formula for our alkenes. The general formula for our alkenes is CN is CnH2n. And it's that straightforward, it's that easy. CnH2n. Whenever we've got a number of carbons, the number of hydrogens in an alkene will always be double. That is CnH2n. So if we had, I think about heptene, and we wanted to figure out how many hydrogens were in heptene, but we wouldn't really have to go through and draw this out and put in all the hydrogens and count them up. We could just use this general formula. We could say, well, I know that hept means that there would be 7 carbons. That's what the prefix stands for. I know that we've got an alkene because it ends in ene. So the alkenes have the general formula CnH2n. So how many hydrogens would I have? Well, let's just sub in 7 for n. When n is 7, we've got C7H2 times 7, which would give us our general formula C7H14. So let's quickly recap what we've talked about. The alkenes are the second homologous series. Their names all end in ene. That's how we can identify them. And by spotting that it ends in ene, it tells us that these structures contain a special bond called a carbon-to-carbon double bond. They've got some uses, the alkenes. They're used mainly as fuels, as solvents, and they're very good starting materials for producing products such as plastics. They're insoluble in water. They're oily. It's just be like trying to mix olive oil and water. You would get 2 different layers. They wouldn't mix together very well. And the general formula, like we've just figured out there, is CnH2n. So different from the alkanes, they've got a different general formula, therefore they're a different homologous series. Now here's our first alkene. It might be maybe a surprise. You might be expecting, well, where's methane? There is no such thing as methane. It doesn't exist because you can't have a carbon to carbon double bond with only 1 carbon. So the first member of the alkene homologous series is not methane, it is ethene. We start with 2 carbons because that's how many we need to get this special carbon to carbon double bond. There's its structure there, as we've seen, and its molecular formula, C2H4. The next member would be propene, again containing a carbon to carbon double bond, and its chemical formula C3H6 fits in with the general formula CnH2n. And that would go all the way down to octene that we would need to know. So we need to know from all the way from ethene to octene for our second homologous series here. Now here's a table that I would like you to have a little look at and have a go at filling it in. We can just look at a wee scrap piece of paper, and I'll go through it in just a second. You can pause the video right now and you can see the answers. So let's look at the answers to this table. First compound here, pentene. Well, pent is 5 carbons, so the molecular formula will be C5. We know the general formula for an alkene, and we know these are alkenes because it ends in ENE. General formula for the alkenes is CnH2n. So when we've got 5 carbons here, we should have double that number of hydrogen, so it should be C5H10. We can check the full structural formula here just to make sure. 1, 2, 3, 4, 5 carbons, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. But you'd rather be able to do it with the general formula. It's going to save you a lot of time doing it that way. Since it's an alkene, it has a carbon-to-carbon double bond, and here it is there. And if we were drawing the shortened structural formula, which is where we don't normally include bonds, we just draw the carbons and what they're bonded to without the actual lines, you will have noticed that the double bond is included here, and that's because it's an important bond. So even though this is the shortened structural formula, when we wouldn't normally include any bonds, if there's a double bond in the compound, we'll pop it in just to make sure we are showing that it is an alkene, and it's a lot more obvious what kind of compound it is. So that's an important bond, so we'll pop that one in. We wouldn't put in any single bonds though into our shortened structural formula. Let's have a little look at the second one then. This time we've not been given a name, we've been given a molecular formula C6H12. Well, when we've got 6 carbons, we know the prefix for 6 is hex. This is looking like it fits into our general formula CnH2n. It's not CnH2n plus 2, so it's definitely not an alkane, it must be an alkene. So this is hexene. And now we can draw it out. We'll pop in our 6 carbons, making sure that we have one double bond, and then between the other carbons just single bonds. And we'll go ahead and fill in the rest of the structure to make sure that every carbon has 4 bonds, and put hydrogens on the end of these open bonds. So there is hexene, the full structure. Remember, our full structure, we show every single bond. Shortened structure, like I said, we need to shorten it down. We'll take away all the single bonds and just leave the important things in, like the atoms, carbon, hydrogen, and any double bonds. So our first carbon here is bonded to 2 hydrogens, so it's CH2. There is a carbon-to-carbon double bond, so I'll pop that in, and then I'll go into the second, third, fourth, and sixth, all the way up to the 6th carbon, and write down what they're bonded to. So here's the second carbon. It is 1C bonded to 1H. And remember, you can just score these out as you go along, just to kind of help you out. Our third carbon here is bonded to 2 hydrogens, so is the 4th and the 5th, so I'll do those 2 now as well. CH2, CH2, and then the last and 6th carbon has 3 hydrogens on it. So there is our completed shortened structural formula, this time for hexene. Heptene, well, hept means that we've got 7 carbons. I know that it is an alkene, must be CnH2n, so it's CnH2n. So it's C7H14. There's the full structure, and we can go ahead and do the shortened structure in the same manner, looking at each carbon and writing down what they are bonded to. First one's bonded to two hydrogens, then we've got a carbon to carbon double bond, and now we've got a carbon bonded to one hydrogen. You might remember last time we did an exercise like this, I said we can use brackets if we've got lots of repeating CH2s, etc. This time we've got 1, 2, 3, 4 CH2s, so instead of writing them out like this, you could also write the CH2s in a bracket and put a little 4 after the bracket, which would tell us that we've got 4 of these CH2s. And then that would take us on to our final carbon, which would be CH3. Now, I said last time that I didn't quite like doing the brackets, but it's totally up to you what method you would do. I don't like doing the brackets just because they look a little bit like a carbon when I write them. And then our last one here is octene, would have 8 carbons in the main chain, making sure that we also have our carbon to carbon double bond, and we can fill in the rest of the hydrogens now as well. Run out of room a little bit, that's fine, don't mind wee mistakes every now and again. And there we go, our full structure for octene. Must have a double bond because it is part of that alkene family. And then I can go ahead and do the shortened structural formula as well, making sure that I am including the carbon to carbon double bond when I'm doing the shortened structural formula. And the last little thing I want to talk about in this video is this idea of saturation again. Now, if you remember back to when we started to talk about the alkenes for the first time, we said that these are saturated compounds, meaning that they only contain single bonds. So the alkanes were saturated, they've only got carbon to carbon single bonds. Well, as we've been talking about for a wee while now, we know that the alkenes, our second homologous series, have a special bond, have a carbon to carbon double bond. So they wouldn't be described as being saturated, they'd be described as being unsaturated. So the alkenes are unsaturated. It means they've got a carbon to carbon double bond. The alkanes, as we said before, they were our first homologous series, they only contain single bonds, so they're saturated. Now, in class or in a lab, you could do a simple experiment to distinguish between these two homologous series, and it's an important experiment. It's one that you have to remember the colour change for, and it's a technique that you have to remember for your SQA exam. And if we wanted to identify between an alkene with a carbon to carbon double bond and an alkane which doesn't have one, you could use a compound called bromine water. Now, if you add bromine water, here's an example of it here, it's a kind of brown colour, a kind of browny yellow colour. If you add bromine water or bromine solution to an alkene, the chemical result would be it would turn colourless. So it would change from being this browny yellow colour to being colourless. Whereas if you added it to an alkane, then it would stay the browny yellow colour. Okay, just to explain that a little bit further in case it wasn't too clear on the last slide, if we wanted to physically test two different liquids to see if one was an alkane or one was an alkene, to test if they were saturated, just single bonds, or if there was an unsaturated carbon to carbon double bond, then we would use a chemical called bromine solution or bromine water. So to test for a carbon to carbon double bond, we would use bromine water. So what you would do, you get two test tubes and put in your liquids and then add a couple of drops of the kind of brown bromine water to each test tube, and that would change the test tubes obviously to a kind of browny orange colour. Now, if we do have, or if the compound rather, does have a carbon to carbon double bond, then the bromine water will turn clear and colourless. So you put it into the alkane test tube where we could have, I don't know, something like propane, where there's no carbon to carbon double bonds, it's totally saturated. The bromine water wouldn't change colour. It would stay this brown yellow colour, wouldn't change. Whereas if we added it to an alkene, which did have a carbon to carbon double bond, well then that carbon to carbon double bond would turn the bromine water from brown back to clear and colourless. There would be a colour change there. And that would be a way that we could use to identify between an alkane and an alkene. And I think that's enough now for this video. We'll look next week into drawing and naming some more complicated alkenes, just like we did with the alkanes. It uses pretty much the exact same rules that we've already learned. There's just a couple of new things to add in, a couple of little things to put in. Hope you guys are all doing well, and I look forward to seeing you all very, very soon.